Today we shall study about electrical energy and power in current electricity. The figure shown in which in a curve electrolytes are placed, resistance are connected, the electrolytes are placed and the two electrodes, positive and negative electrodes. Now we explain it, how the energy is created and distributed, transmitted. The energy dissipated per unit time is the power dissipated P, our delta W by delta T, and we have P our IV. The delta W is the small increment in power and delta D is the small increment in time. Using Ohm's law, V our IR, we get P our I square R brought V square by R as the power loss, ohmic loss in a conductor of resistance R carrying a current I. It is a power which heats up. For example, the coil of an electric bulb to incandescent radiating out heat and light. Where does the power come from? Where does the power come from? We need an external source to keep a steady current through the conductor. It is clearly this source which must supply this power. It is clearly the source which must supply this power. In the sample circuit shown with a cell in the figure 1, it is a chemical energy which supplies this power for as long as it can. The equation has an important application to power transmission. Electrical power is transmitted from power station to homes and factories, which may be hundreds of miles away, via transmission cables. One obviously wants to minimize the power loss in the transmission cables connecting the power station to homes and factories. We shall see now how this can be achieved. Consider a device R to which a power P is to be delivered via transmission cables having a resistance RC to be dissipated by it finally. If V is the voltage across R and I is the current through it, then P or VI. The connecting wires from the power station to the device has a finite resistance RC. The power dissipated in the connecting wire which is pasted with PC barabar I square RC barabar P square RC by V square. Thus to drive a device of power P, the power pasted in the connecting wire is inversely proportional to V square. The transmission cables from power station are hundreds of miles long and their resistance RE is considerable. To reduce PC, these wires carry current at enormous values of V, and this is the reason for the high voltage danger sign on transmission lines. A common sight as we move away from populated areas using electricity at such voltages is not safe, and hence at the other end a device called a transformer lowers the voltage to a value suitable for use. Now the combination of resistance, series and parallel, the series combination. As shown in the figure, two resistance R1 and R2 are connected, current I is flowing in series. Potential difference of R1 बराबर I R1, potential difference of R2 बराबर I R2, I the current flowing in wire, so the total potential difference बराबर I R1 plus I R2. So I R बराबर I R1 plus I R2, so R बराबर R1 plus R2. When R is equivalent resistance of R1 and R2, it is series combination. It can be extended to n resistance. इसलिए R n बराबर R1 plus R2 dash dash n. Parallel combination. As shown in the figure, two resistance R1 and R2 are connected parallel. Their one end is A and the other end B. Current entering to the circuit from point A and going outside from point B. Here the potential difference is constant, but the current is different from the resistance. The resistance R1 and R2 are connected in parallel. Current I flows from A to B, so I बराबर I1 plus I2. Therefore, I1 बराबर V बटा R1, where V is the potential difference between A and B, and I2 बराबर V बटा R2. इसलिए I बराबर V बटा R1 plus V by R2 बराबर V by R, where I is equivalent resistance. इसलिए 1 by R is equal to 1 by R1 plus 1 by R2. For n resistance, 1 by Rn बराबर 1 by R1 plus 1 by R2 plus dash n, है ना, 1 by n. Now, cells, EMF and internal resistance. In the figure shown of a cell, it has two electrodes called positive P and negative N. They are immersed in an electrolyte solution. Dipped in the solution, the electrodes exchange charges with the electrolyte. The positive electrode has a potential difference V plus is greater than 0 between itself and the electrode solution immediately adjacent to it, marked A in the figure. Similarly, the negative electrode develops a negative potential minus V minus is greater than 0 relative to V. Electrolyte adjacent to it, marked as B in the figure. When there is no current, the electrolyte has the same potential throughout, so that the potential difference between P and N is V plus minus V negative barabar V plus V N. The difference is called the electromotive force or EMF of the cell and is denoted by E. So, E बराबर V plus V N is greater than 0. E is a potential difference, not a force. The name EM used because of historical reason and was given at a time when the phenomena was not understood properly. To understand the significance of E, consider a resistor R connected across the cell. A current I flows across R from C to D. STD current is maintained because current flows from N to P. So the electrolyte clearly across the electrolyte the same current flows through the electrolyte, but from N to P, whereas through R it flows from P to N. The electrolyte through which a current flows has a finite resistance, a small r, called the internal resistance. Consider first the situation when R is infinite, so that I or V what R is equal to 0, where V is the potential difference between P and N. Now V without potential difference between P and A plus potential difference between A and B plus potential difference between B and N is equal to E. Thus, EMF E is the potential difference between the positive and negative electrode in an open circuit. It means when no current is flowing through the cell, if R is finite, I is not zero. In that case, the potential difference between P and N is V barabar V plus V in minus IR barabar E minus IR. Note that the negative sign in the expression IR for the potential difference between A and B. This is because the current I flows from B to A. In the electrolyte, in practical calculations, internal resistance of cells in the circuit may be neglected when the current I is such that E is very greater than R. From Ohm's law, V barabar IR barabar E minus IR or I barabar E bata R plus R. The maximum current that can be drawn from a cell is for R barabar 0 and it is maximum E bata small r. However, in most cases, in most cells, the maximum allowed current is much lower than this to prevent permanent damage to the cell or charges in cloud. The electric field is of the order of 10 to the power 5 volt per meter. Duration of each flash is 50 seconds. Is 30 seconds. The average peak power per stroke is about 10 to the power 12 watts. The electric field is 120 volt per meter. Surface charge density is minus 1.2 10 to the minus 9 coulomb per meter square. Total negative charge is 600 kilocoulomb. An equal positive charge exists in the atmosphere. This electric field is not noticeable in daily life.